Hello again. So today I will try to make a reheat Rankine cycle. It was a request from one of the comment in one of my other video. So let's start without wasting any time. And one thing which I will do is I will try to make the model flexible, because I want to make my models flexible so that I can change any inputs and outputs and I don't need to change so much other things. So I will be using controller block and specification block there also to see how we can reach or achieve certain outputs with changing certain inputs. I have one of my problem which I took it from my master studies in renewable energy, where there is a 200 megawatt power plant and there are two steam turbines, high pressure steam turbine and low pressure steam turbine. So if you follow stream 1, where steam at 180 bar and 550 degrees Celsius is entering into high pressure steam turbine and leaving at 40 bar, then going back to the boiler again and enters into the second low pressure or medium pressure steam turbine after reheating to 550 degrees Celsius again, and then it leaves at 0.04 bar to condenser pumped back to the boiler. In the boiler they are using lignite, so there are some restrictions in DWSIM and where we cannot use solids, or it will be difficult to use solid lignite, so I will be using natural gas fuel here. And the boiler efficiency is 90%. That's information we have. We also have information that there are isentropic efficiencies of steam turbines are 85 or 87%. Mechanical efficiency is 96%, which I guess there is no option to use in DWSIM, so we will avoid it. So what I will do by using DWSIM, I will first calculate the mass of steam required to produce 200 megawatt in this reheat cycle, and then what is the mass of natural gas fuel to produce that amount of steam. So let's start it. New chemical process model. So I assume you already know a little bit about DWSIM, so I'm not explaining everything. You need to add compounds. With methane I will add water for steam cycle and also for methane combustion. Then we need air, so I am using oxygen and nitrogen for air. Then carbon dioxide after combustion of natural gas. For properties packages we'll go with Bang-Robinson, and system of units I will go with custom one. Temperature degree C, mass flow rate kilogram per second, pressure bar is fine, and energy flow in megawatt. And then we will start. And first we'll go with steam cycle, so we need two steam turbines and we need reheater, and we will add the boiler heat exchanger later. And I will close that auto connect option because I like to do my own connections. We'll go with pressure changers and expander. One steam turbine, second steam turbine, we will name them HPT and LPT respectively. And if you know DWSIM, you need to know that when you press or type anything you need to press enter, otherwise it will not use as an input. We'll make connections, inlet, outlet and energy. As there is a reheater there, so we will need heat exchanger. Heat exchanger will take stream 2 as an input. Outlet stream will connect and we need energy. Low pressure stream will take outlet of reheater and will create fourth stream. We need energy stream. And then there will be condenser, so I am using simple cooler. It will take stream 4 as an input and will create another stream output and then energy stream. And then we need pump, again pressure changers. Pump, it will take stream 5 as an inlet. Outlet we will create and energy. So we can start inputs, as it will only be water as a stream, so we will clear existing compound mole fractions and enter 1 for water, accept changes, and stream conditions will keep it 1 kilogram per second, or let's make it 50 kilogram per second. Pressure will be 180 bar as given in the problem, and temperature was 550 degrees Celsius. In high pressure stream turbine, the outlet pressure was 40 bar if you remember, and efficiency of gas turbine was 85%. Then in reheater, it was reheated to outlet temperature of 550 degrees Celsius again, and in low pressure steam turbine, outlet pressure was 0.04 bar. And in condenser, we will change it to outlet vapor mole fraction, so we are condensing it everything, so it will be 0. And then in pump, we will have outlet pressure of again 180 bar and will take efficiency of 90%. So if you see a 550 degrees Celsius of steam entered into the high pressure steam turbine, and outlet conditions, it will be at 319 degrees Celsius, 40 bar. It will be reheated again to 550 degrees Celsius. So you go to stream 3 at 40 bar and then enter into the low pressure steam turbine. Yes, and then you see we are getting 17 megawatt of electricity from high pressure steam turbine, around 18 megawatt, and 52 megawatt around from low pressure steam turbine. In total it is 51, 17, 68 and 70 megawatt, but the problem states we have 200 megawatt of power plant. So either you can just do hit and trial, add water flow rate 200 and add how much is it, or you can use now it's 53 and 154 around 200, so you can play with that. Or what you can also do, you can go to you can use the logical block from DWSIM controller, logical blocks and controller here. Before, efficiency of second steam turbine was not 75%, it was 87%, so that's there. So with controller block, we want to manipulate mass flow rate and we want to control the power for E1 plus E3 should be 200. And the main problem with DWSIM now here is it does not have mixer for energy as compared to Aspen Plus. It would have been easy if we just mix both energy streams and we can control that energy stream there, but there is a workaround for that. We'll go script manager and write new script, and there we will add an energy stream. It will be E6. Just remember it's E6. So we will write E6 dot energy flow is equal to E1 dot energy flow plus E3 dot energy flow. We will run it. Go back to the flow sheet. See, now it is giving total of energy from E1 plus E3. We'll make some other changes there. We will link it to object E6 or simulation. Okay, I think we need to link object solver with solver finished, and we'll see how it behave. Go to flow sheet. With controller we need to manipulate mass flow rate from 1, and we need to control E6 energy flow. We need to make it 200 megawatt, and let's reduce the tolerance a little bit. We will use Newton method for first. Let maximum iterations, make it 200 and start adjusting it. It is not working. So I guess from script manager you just use any object E1 and then event object calculation finished, and go back to the flow sheet. And again, I think I missed. I need to press enter by writing 200 and then start adjust. Yes, now calculations are finished. So we need around 128.832 kilogram per second of steam to produce 200 megawatt of power. So you can just add, for example, what if you need 250 megawatt of power, how much steam will be required? So you need around 161 kilogram per second. We can make certain changes also. For example, pump power is also subtracted from total power, so we can go to script manager again and minus E5 dot energy flow. Run it, go to the flow sheet, and then again start adjusting it. Remember, it was 128 kilogram per second. Now it's 130.5 to 1 kilogram per second of steam is required. And now we can go to the second part, how much natural gas would be required to produce that 130 or 131 kilogram per second of steam. So we already had one reheater, so we need to add the boiler there also. So reheater has been added, which is consuming 67.5 megawatt of heat. So there must be another heat exchanger heater. So what I will do, I will go to the HPT and disconnect stream 1, add it to inlet stream of H1, add second stream there, and use 7 stream there. So now let's assume stream 1 is coming back at the same conditions from where the pump is leaving. So at pump it has been left at 28.5 degrees Celsius and 180 bar. So 28.5 degrees Celsius, 180 bar, and in heater it has been added to 550 degrees Celsius. So now we can run the calculator block again to see if it changes little bit. No, it is fine. But heater we forgot to add energy stream. And now we can run the calculator controller block again. Yes, it is fine. So if you see, we need 436 megawatt of heating plus 67 megawatt of heating. So in total 400 for 67 plus 36, around 505 megawatt. But we also know boiler is 90% efficient, so we will add another energy stream and add another script. Go to the script manager and we'll see this is E8. E8 is E7 plus E2 divided by 0.9. E8 dot energy flow is equal to E2 dot energy flow plus E7 dot energy flow divided by 0.9. I will link it with, let's see, E2 object calculation finished, and run it. Go to the flow sheet. Now we see 559 megawatt of power is required from natural gas. So we'll start building our natural gas combustion section. We need reactor. Let's start with conversion reactor. It's easy to model combustion in conversion reactor. Before that, we need fuel, and we also need air. And then we go to add stream mixer, where we will mix both fuel and air. There's also one of the problem with DWSIM. It does not have two inputs in conversion reactor as it is. So we need to first mix both fuel and air and then use that mixture in reactor. So we added stream 10 there. We have to have two outlet streams and one energy stream. For fuel, we will change compound amounts. Clear, we will take 100% methane, accept changes. Stream condition, let's see, it 1 is fine. With air, just assume simplest form of air with 21 mole % oxygen and 79 mole % nitrogen, accept changes. Air will also be at 25 degrees Celsius and 1 bar. Let's assume mass flow rate of 5 kg per second. For conversion reactor, we need to add a reaction set. So we go to settings. We'll go to reactions, add conversion reaction. Methane is included, water is included, oxygen is included, and carbon dioxide is included. Stoichiometry, if you know the methane combustion reaction is CH4 plus 2 water, so -1, -2, 2 moles of water will be produced by consuming -2, and carbon dioxide will be 1. So if you see stoichiometry is okay. CH4 plus 2 moles of oxygen are reacted to produce 2 moles of hydrogen and 1 mole of carbon dioxide. If you don't know the reaction, just go to the Google and find this coefficient. Just remember, if it's a reactant, then it's minus. If it's a product, it's plus. And if it's not okay written there, then it means your stoichiometry is not in balance. For example, if I write 3 there, it doesn't make sense. So you need to add the base component. I add methane there. Will be base component, phase will be vapor, and conversion will be 100%. So reactions set will be default set. Calculation mode will be adiabatic, and then we can solve it. So you see it is being solved, and the temperature of outlet is 1482 degrees Celsius. and it will have zero amount of oxygen. It means we are not providing enough oxygen and all the oxygen is consumed there. Water, methane is 18% methane is still unreacted. So what we can do, we can have a specification block to provide the amount of oxygen required. There are so many ways. This is the very easiest way, not the recycle block. I need specification block. Where source object is fuel and source property is mass flow, target object is air and its mass flow, and calculation mode is global setting. So y is air, target object. So normally it is 17.5 kilogram per second of fuel is required for every kilogram per second of methane, and we are adding 50% excess here, so I am multiplying it with 1.5, and then if I solve it, it's being solved, and if you see now methane is 0 and oxygen is present, so we are on the right track. So you can also specify that there must be, or you can control block, there must be some amount of oxygen left here by changing amount of air there, but that can be complicated. This is the easiest way. So now we need to add another cooler. So you will know why we need cooler in a bit. So if we add cooler there and take stream 11 as input and just add another stream and create energy stream also. So in cooler, instead of heat adit removed outlet temperature, let's assume it's 130 degrees Celsius and energy flow is 46 megawatt. So now we can go and add a controller block. Let's see if the model will converge. So I'm trying this also first time. So we will manipulate fuel. Let's see how did we do it previously. We manipulated, yes, we will manipulate fuel, and by controlling this E10. So we will manipulate fuel and we will manipulate its mass flow rate. By doing so, we will manipulate control E10, its energy flow, and we want to make E10 559.92 megawatt. Press enter. Tolerance, let's reduce it more. Use Newton method, maximum iteration to 100. Maximum limits, let's make it 20 and start adjusting it. It might take some time. No, he did it. Good. So 11.93 kilogram per second of fuel is required to provide 559 megawatt of steam, which can be used, which was used by steam turbines. So now we have the basic mass balance for whole plant, and now you can instead of making it complicated or long, you can just have it by using simple heat exchangers there, and where you can just use shell and tube heat exchanger model there, which I'm not doing it for this exercise. It is already being so long now, like video is long now, but you can play a little bit around with everything, and you can also add a recycle block with 6 and 1 and recycle it, but I did it so that I do not want to make the convergence difficult. But this is how you just play around with this tool and just do your simulations and do your exercises and assignments. And if you have any request, if you want to make some changes here, just write in comments. And if you like my content, let's subscribe, and I will try to make some other videos in Python also and in Aspen Plus also. Till then, bye bye.